Hello, in this lecture I'll answer two questions. In the first question, we find out the area of this big rectangle EFQH, and in the second question, we find out the area of this circle using two different methods. So we start with the first question. In the drawing we have this big rectangle EFQH. Inside this rectangle we have three circles, and the radius of this small circle is 5, the radius of this medium circle is 6, and the radius of this big circle equals to 8 units in its length. Again, our task is to find out the area of this big rectangle EFQH. So first of all, we know that all the angles in a rectangle are right angles. So those four angles are all right angles. So this is a right angle. This is also a right angle. This is a right angle. This is a right angle. So here you can implement rule 1 in our drawing. So repeat quickly rule 1. According to rule 1, a tangent to a circle is perpendicular to the radius drawn to its point of tendency. In the drawing, we have a circle. This is tangent AB, that is tangent to the circle at point M. In addition, we have the radius OM that is equals to R. The radius OM is drawn to point M, that is the point of tendency of tangent AB with this circle. And whenever your radius is drawn to the point of tendency, then tangent AB will be perpendicular to the radius MO. If AB is perpendicular to MO, it means that this angle equals to 90 degrees, and this angle also equals to 90 degrees according to this rule 1. So we will implement rule 1 a lot of times in our drawing. So we'll explain only one time how we can implement rule 1, and in the other cases we will implement rule 1 automatically without any explanation. For example, we take this medium circle. The radius of this medium circle QB equals to 6. The radius QB is equals to 6. The radius QB is drawn to point B, that is the point of tendency of tangent HQ with this medium circle. And whenever you have a radius that is drawn to the point of tendency, then tangent HQ will be perpendicular to the radius BQ. If HQ is perpendicular to BQ, it means that this angle equals to 90 degrees. And this angle also equals to 90 degrees according to rule 1. According to rule 1, this angle equals to 90 degrees. And this angle also equals to 90 degrees. Likewise, according to the sum rule, this angle equals to 90 degrees, and this angle also equals to 90 degrees. In the next step, we define the point of tendency of tangent FQ with this big circle. This point is point T, and we join points S and T together by a straight line. ST is of course the radius of this big circle, is equals to 8. According to rule 1, this angle equals to 90 degrees, and this angle also equals to 90 degrees. In the small quadrilateral CFTS, we have 1, two free right angles. The sum of free right angles is 270 degrees. So 270 degrees plus the size of this 4th angle, in total they must be equal to 360 degrees according to the rule that the sum of the angles in any quadrilateral is equal to 360 degrees. And therefore this 4th angle must be equal to 90 degrees in its size. So beside the small quadrilateral FCST we have 4 right angles. Therefore we can relate to quadrilateral FCST is a rectangle. But we also know that the opposite sides of a rectangle are equal to each other. So in rectangle FCST, side ST equals to the opposite side CF. But ST equals to 8, therefore the opposite side CF must be also equal to 8 units in its length. In the next step, we define the point of tendency of tangent HQ with this big circle. This point is point L. And we join points S and L together by a straight line. SL is of course the radius of this big circle, that is equal to 8 units in its length. By joining the points S and L, we created the lower quadrilateral STQL. But before that, according to rule 1, this angle equals to 90 degrees, and this angle also equals to 90 degrees. So in the lower quadrilateral STQL, we have 1, 2, 3 right angles. And therefore this 4th angle must be equal to 90 degrees in its size. So the big angle CSL, this is the big angle CSL, that is equal to 90 degrees plus 90 degrees is 180 degrees. And we know that any angle that is equal to 180 degrees in its size, it is defined as a straight line. Therefore CL is a straight line. So the norm CL is a straight line. So we have shape EC and edge. In shape EC and edge we have 1, 2, 3, 4 sides, and therefore shape EC and edge is a quadrilateral. Okay, because it has 4 sides. In quadrilateral EC and edge, this is quadrilateral EC and edge, we have 4 right angles, 1, 2, 3, 4. And any quadrilateral that has 4 right angles must be at least a rectangle, if not a square, so we have to quadrilateral EC and edge as a rectangle. But we also know that the opposite sides of a rectangle are equal to each other. But you know that EC and edge is a rectangle. Because it has 4 right angles. But we also know that the opposite sides of a rectangle are equal to each other. So in the big rectangle EC and edge, side CL must be equal to the opposite side EH, but CL in total is 8 plus 8, it is 16. Therefore the opposite side EH must be also equal to 16 units in its length. EH is the width of the big rectangle EFQH, so we found out actually that the width of this rectangle EFQH is equal to 16 units. The only thing that is left to find is to find the length EF, and the width times the length is equal to the area that we are looking for. This question that is the area of the big rectangle EFQH. In the next step, we will extend the radius BQ of the medium circle by a straight line until it touches side EF of the big rectangle, and we define the touching point of the extended radius BQ with side EF. This point is point M. When doing this construction, we're gonna do quadrangle EMB edge. Inside quadrangle EMB edge, we have 1, 2, 3 rectangles, and therefore this fourth missing angle must be equal to 90 degrees in its size. Likewise, we also created quadrangle MCLB. This is quadrangle MCLB. In quadrangle MCLB, we have 1, 2, 3 rectangles, and therefore this fourth missing angle must be equal to 90 degrees in its size. So quadrangle MCLB is a rectangle because it has 4 rectangles. But we also know that the opposite sides of a rectangle are equal to each other. So rectangle MCLB, side CL must be equal to the opposite side MB. But CL is 16, 8 plus 8 is 16. Therefore, MB must be also equal to 16 units in its length. MB equals to 16 units in its length. In the next step, we will do another construction. That is to say, from this point P, that is the center of this small circle, we will do perpendicular on MB. Okay, from point P, we will do perpendicular on MB. So actually, this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. We define the touching point of the perpendicular from point P and MB. This point is point K. When doing this construction, we created the small quadrangle AMKP. This is quadrangle AMKP. This quadrangle, small quadrangle AMKP, we have 1, 2, 3 right angles. Therefore, this fourth missing angle must be equal to 90 degrees in its size. Quadrangle AMKP is 4 right angles. Therefore, we can relate to quadrangle AMPK is a rectangle. But we also know that the opposite sides of a rectangle are equal to each other. So in the small rectangle AMKP, side AP must be equal to the opposite side MK. But AP is 5, therefore the opposite side MK must be also equal to 5 units in its length. What is the length of this missing line segment? Line segment KQ. From the drawing it is very easy to see that KQ in total equals to MB minus MK minus QB. So KQ in total equals to MB is 16 minus MK is 5. 16 minus 5 is 11 minus QB is 6, and 11 minus 6 is 5. So if we found out that the missing line segment KQ is equal to 5 units in its length. This is the missing line segment KQ is equal to 5 units in its length. In the next step, we will join points P and Q together by a straight line. Point P is the center of this small circle. Point Q is the center of this medium circle. So PQ is the distance between the centers of those two circles. We have an external notch between the small circle and the medium circle at this point. This is their touching point. We will define their touching point. This point is point O. And whenever you have an external notch between two circles, you can implement rule 10. So I click quickly on rule 10. According to rule 10, if two circles touch each other externally, then the straight line that connects their centers together passes through their touching points. So in the moment we have two circles that touch each other externally at point K. This is point K. It is their touching point. The center of this circle is here at point O. The center of this circle is here at point M. And the straight line that connects the centers together is of course the straight line OM. And according to this rule 10, the straight line OM must pass through their touching point, that is point K. Again, according to rule 10, the straight line OM that connects the centers together must pass through point K, that is their touching point. Or in other words, OKM is one straight line. OKM is one straight line according to this rule 10. We can implement rule 10 in our drawing. In our drawing, we have an external notch between the small circle and the medium circle is point O. According to rule 10, the straight line that connects their centers together, that is the straight line PQ, must pass through point O, that is their touching point. Or POK is one straight line. POK is one straight line according to rule 10. PO is the radius of this small circle that is equal to 5. QO is the radius of this medium circle that is equal to 6. And if POQ is one straight line, it means that PQ will be equal to PO plus OQ. Again, PQ will be equal to PO, that is 5, plus OQ, that is 6. 5 plus 6 is 11. So PQ equals to 11 units in its length. Or in other words, the distance between the centers of the small circle and the medium circle is 11 units. In the next step, I'll copy the right green triangle PKQ in a new page, and we will implement the Pythagoras theorem on this right green triangle PKQ. According to the Pythagoras theorem, in any right triangle, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. Side KQ equals to 5 units in its length, and the hypotenuse PQ equals to 11 units in its length. PK is the missing side. Here by PT is the permission for Pythagoras theorem. So actually, this is the right green triangle PKQ that the coordinate from the original drawing. This right triangle PKQ, according to the Pythagoras theorem, PQ squared, that is the square of the hypotenuse, is equal to PK squared plus KQ squared. So I write it down. PQ squared, that is the square of the hypotenuse, equals to PK squared plus KQ squared. The hypotenuse PQ equals to 11 units in its length, therefore PQ squared is 11 squared, that is 121, and it is equals to PK squared. PK is the missing side, so we leave it as it is. So it is PK squared plus KQ squared. KQ is 5, therefore KQ squared is 5 squared, that is 25. So in total we should find out that 121 equals to PK squared plus 25. Here we will subtract 25 from this equation, and we get that 121 minus 25 is 96. So 96 equals to PK squared. Here we will substitute 96 by 16 times 6. We substitute 96 by 16 times 6. So 16 times 6 equals to 96. 16 times 6 equals to PK squared. So here we take a root out of this equation, and finally we get that the missing side PK is equal to the square root of 16, that is 4, so inside the root we left only with 6. So the length of the missing side PK is equal to 4 times square root of 6 units in its length. This is the missing side PK, that is equal to 4 times square root of 6 units in its length. We have already found out that AMKP is a rectangle, and we know that the opposite sides of a rectangle are equal to each other. So in the small rectangle AM KP side PK must be equal to the opposite side AM. But PK is 4 times root of 6, therefore the opposite side AM must be also equal to 4 times root of 6 units in its length. In the next step, we will define the point of tendency of tangent E edge with this small circle. This point is point X, and we'll join points P and X together by a straight line. Px is of course the radius of this whole circle is equals to 5. According to rule 1, this angle equals to 90 degrees, and this angle also equals to 90 degrees. So in the small quadrilateral EAPX we have 1, 2, 3 right angles, and therefore this fourth angle must be equal to 90 degrees in its size. So in quadrilateral EAPX we have 4 right angles, and therefore we can relate to quadrilateral EAXP is a rectangle. But we also know that the opposite sides of a rectangle are equal to each other. So in the rectangle, in the small rectangle EAXP, side XP must be equal to the opposite side EA. But XP is 5, therefore the opposite side EA must be also equal to 5 units in its length. In the next step, we will join points Q and S together by straight line. Point Q is the center of this medium circle, point S is the center of this big circle. We have an external mesh between this medium circle and this big circle at this point. We define this point, that is the touching point, as point Y. You can implement here rule 10. Whenever you have an external mesh between two circles, you can implement rule 10. The straight line that connects the centers of those two circles together is of course the straight line SQ. And according to rule 10, the straight line SQ must pass through the attaching point, that is point Y. Again, the straight line SQ must pass through point Y, that is the attaching point, or SYQ is one straight line. SYQ is one straight line. If SYQ is one straight line, it means that SQ in total must be equal to SY plus YQ. So SQ equals to SY. SY is the radius of this big circle, that is 8, plus YQ. YQ is the radius of this medium circle, that is equals to 6 units. So total XQ must be equal to SY, that is 8, plus YQ, that is 6. 8 plus 6 is 14. So SQ equals to 14 units in its length. In the next step, we will do another construction, that is to say, from this point Q, that is the center of this medium circle, we will do perpendicular on CL. Again, from point Q, we will do perpendicular on CL. So actually this angle equals to 90 degrees. And this angle also equals to 90 degrees according to our construction. We define the touching point of the perpendicular from point Q and CL. This point is point J. by doing this construction, we get in there the small quadrangle QJLB. Inside the small quadrangle QJLB, we have 1, 2, 3 right angles, and therefore this 4th angle must be also equal to 90 degrees in its size. So inside quadrangle QBLJ, we have 4 right angles, and therefore we can define quadrangle QBLJ as a right angle because it has 4 right angles. But we also know that the opposite sides of a rectangle are equal to each other. So the lower rectangle QBLJ, side QB must be equal to the opposite side JL. But QB is 6, it is actually the radius of the medium circle. Therefore the opposite side JL must be also equal to 6 units in its length. JL equals to 6 units in its length. What is the length of this small short line segment SJ? SJ equals to SL minus JL. Again, SJ equals to SL minus JL. So already known. SJ, the short line segment SJ, equals to SL minus JL. So SJ equals to SL. SL is the radius of this big circle that is 8 minus JL. We just right now found out that JL equals to 6. So HJ in total equals to 8 minus 6, that is 2. SJ equals to 2 units in its length. In the next step, I'll copy the right green triangle QSJ in a new page, and we will implement the Pythagoras theorem on this right green triangle QSJ. The hypotenuse QS equals to 14 units in its length, side SJ equals to 2 units in its length, and QJ is the missing side. Here by PT is the abbreviation for Pythagoras theorem. So actually, this is the right green triangle QSJ that occurs from the original drawing. This right triangle QSJ, according to the Pythagoras theorem, QS squared, that is the square of the hypotenuse, must be equal to SJ squared plus JQ squared. So already known. QS squared, that is the square of the hypotenuse, is equal to SJ squared plus QJ squared. QS equals to 14, therefore QS squared equals to 14 squared. that is 196, equals to Sj squared. Sj is 2, therefore Sj squared is 2 squared, that is 4, plus Qj squared. Qj is the missing sign, so we leave the city, so it is plus Qj squared. In total, we should find out that 196 equals to 4 plus Qj squared. Here we will subtract 4 for this equation, and we get that 196 minus 2 is 192 equals to Qj squared. Here we will substitute 192 by 64 times 3, and we get that 64 times 3 equals to Qj squared. So here we take a root out of this equation, and we get that the missing side Qj is equal to the square root of 64, that is 8, and inside the root will have to only be 3. So in total we should find out that the missing side Qj is equal to 8 times square root of 3 units in its length. So here, this is the missing side Qj, that is equal to 8 times square root of 3 units in its length. So in quadrilateral MCJQ, we have 1, 2, 3 right angles. Again, we have 1, 2, 3 right angles. And therefore this fourth missing angle must be equal to 90 degrees in its size. Therefore we can relate to this quadrilateral MCJQ as a right angle because it has 4 right angles. But we also know that the opposite sides of an rectangle are equal to each other. So in rectangle MCJQ, side QJ must be equal to the opposite side MC. But QJ is 8 times square root of 3, therefore the opposite side MC must be also equal to 8 times square root of 3 units in its length. So if we found out that the length of this rectangle EFQH, the length is EF, and EF in total equals to 5 plus 4 times square root of 6 plus 8 times square root of 3 plus 8. And the width is EF, is EH, is equals to 16 units in its length. And the width times the length is the area of this rectangle EFQH. So it's done. We actually found out that the area of this big rectangle EFQH, that is the area that we are looking for in this question. Is equal to the width times the length. It is true in any rectangle, therefore it is true in this rectangle EFQH. So the area of the big rectangle EFQH, that is the area that we are looking for in this question, it is equal to the width times the length. The width is the edge, again, the width is the edge, and the length is the F. The length is the F. So the area of the big rectangle EFQH equals to the width that is the edge times the length that is the F. EH, the width EH equals to 16 units in its length. and the length EF equals to EA plus AM plus MC plus CF. So total we found out that the area of the big rectangle EFQH equals to the width, that is 16, times the length, that is EA plus AM plus MC plus CF. So the area of the big rectangle EFQH in total equals to 16 times EA is 5, plus AM is 4 times square root of 6, plus MC is 8 times square root of 3, plus CF is 8. So in total we found out that the area of rectangle EFQH equals to 16 times 5 plus square root of 6 plus 8 times square root of 3 plus 8. Actually, the value of this expression in total, it is equals to 586.47 square units in its size. So we found out that the area that we are looking for in this question, that is the area of this big rectangle EFQH, is equal to 586.47 square units in its size. So we finished with the first question. In the next step, I will present to you the second question, and we'll solve the second question by using two different methods. Our task in the second question is to find out the area of this big circle. In the moment we have a circle, this is called AB, that equals to 8 units in its length. This is called PQ, that is equals to 6 units in its length. This is angle PMQ, that is equals to 90 degrees in its size. Again, our task is to find out the area of this circle. So first of all, I will present to you Rule 29, and we will implement Rule 29 in our drawing. According to Rule 29, peripheral angles that subtend on the same arc are equal to each other in their sizes. So, in the drawing a circle, and this is peripheral angle BDC, that is equal to alpha degrees in its size, and it subtends on arc BC. Again, peripheral angle BDC subtends on arc BC. Likewise, we have another peripheral angle. This is peripheral angle PAC. This is equal to beta degrees in its size, and it's subset on the same arc BC. And because of the fact that those two peripheral angles, they both subset on the same arc BC, they must be equal to each other in their sizes. This is to say alpha equals to beta. So according to this rule 29, if two or more peripheral angles subset on the same arc, they must be equal to each other in their sizes. So we can implement Rule 29 in our drawing. Why? Because in our drawing, if we focus on this arc BQ, the red curve BQ is arc BQ. We have peripheral BAQ that subtend on arc BQ. Again, peripheral BAQ, this peripheral subtend on the arc BQ. Likewise, we have another peripheral. This is peripheral BPC, PPQ. This is peripheral BPQ that subtend on the same arc BQ. And because of the fact that those two peripherals subtend on the same arc BQ, they must be equal to each other in their sizes. So if we define the size of this angle as alpha, then the size of this angle must be equal to alpha because they are equal to each other according to Rule 29. In the next step, we'll focus on this arc AP. This is RKP, and this is peripheral PQA that subtend on RKP. Again, peripheral PQA subtend on this arc RKP. Likewise, we have another peripheral, that is peripheral ABP, that is also subtend on the same arc RKP. And because of the fact that those two peripherals are both subtend on the same arc RKP, they must be equal to each other in their sizes. So if we define the size of this peripheral AQP as beta, then the size of this peripheral ABP must be also equal to beta because they are equal to each other according to Rule 29. Those two angles are defined as vertex angles, and we know that vertex angles are equal to each other. But this angle equals to 90 degrees, and this angle must be also equal to 90 degrees because they are equal to each other. So in the right angle A and B, the sum of the angles must be equal to 180 degrees. It is true in A triangle, and therefore it is also true in the right angle A and B. So which angles we have in the right angle A and B? Alpha plus beta plus 90 degrees, in total they must be equal to 180 degrees. Here we will subtract 90 degrees from this equation, and we will get that alpha plus beta equals to 180 degrees minus 90 degrees is 90 degrees. So alpha plus beta equals to 90 degrees. Here we will multiply this equation by 2, and we will get that alpha plus beta equals to 90 degrees times 2 is 180 degrees. Again, we multiply this equation by 2, and we get that 2 alpha plus 2 beta equals to 90 degrees times 2 is 180 degrees. So in total we found out that 2 alpha plus 2 beta equals to 180 degrees. We define the center of this circle. This point is point O. In the next step I will present to you Rule 13, and we will implement Rule 13 in our drawing. According to Rule 13, a central angle is twice as large as the peripheral angle subtended on the same chord. It doesn't matter if you are talking about a chord or arc. So it is on the same chord or the same arc. Because if it's subtended on the same arc RKB, it is also subtended on the same chord on the same chord called AB. So in the normal we have a circle. This is peripheral angle ACB is equals to theta degrees in its size, and peripheral angle ACB subtend on RKB. Likewise, we have center angle AOB that subtend on the same arc RKB. According to this rule 13, the size of the center angle AOB that subtend on the same arc RKB, like this peripheral angle AOB, must be twice as big as the peripheral angle that subtend on the same arc RKB. So the size of the peripheral angle is theta, and therefore the size of the center angle that subtended on the same arc RKB must be equal to 2 theta. So according to rule 13, the size of the center angle is twice as big as the size of the peripheral angle that subtended on the same chord or arc. Okay, so we can implement rule 13 in our drawing. We know that the center angle is its vertex is in the center of the circle, that is to say from point O, and its two legs are the two radii of the circle. So we create peripheral angle AOP. We created a center angle AOP. It is a center angle because its vertex is at point O, that is the center of the circle. OP is one leg, that is the radius of the circle. OA, the second leg, that is also the radius of the circle. So angle AOP is a center angle that subtend on RKP. Again, angle AOP is a center angle that subtend on RKP. But we also have peripheral angle AQP also subtend on the same arc RKP. And therefore, according to rule 13, the size of the center angle AOP is twice as big as the size of peripheral angle AQB that is subtended on the same arc RKP. The size of peripheral angle AQP is better, and therefore the size of the center angle AOP that is subtended on the same arc RKP must be equal to 2 beta. So it's twice as big as the size of this peripheral angle that's subtended on the same arc RKB. In the next step, we create another center angle. This is center angle BOQ. This is center angle BOQ that subtend on arc BQ. Again, center angle BOQ subtend on arc BQ. Likewise, we have peripheral angle BAQ that is subtend on the same arc BQ. And according to rule 13, the size of peripheral angle, the size of the center angle BOQ that subtend on the same arc BQ, exactly like peripheral angle BOQ, it must be twice as big as this peripherical BAQ. The size of peripherical BAQ is alpha, therefore the size of the third triangle BOQ must be equal to 2 alpha according to rule 13. In the next step, we will define the size of this angle QOP as x, and we define the size of this third angle BOA, this angle as y. We have the rule that says that the sum of the angles around any point is equal to 360 degrees. I repeat again, the sum of the angles around any point is equal to 360 degrees. So the sum of the angles around this point O, that is the center of the circle, must be equal to 360 degrees. So which angles we have around point O? We have this angle that is 2 alpha plus 2 beta plus x plus y. In total, the sum of those 4 angles must be equal to 360 degrees. But we have already found out that 2 alpha plus 2 beta equals to 180 degrees. Here, 2 alpha plus 2 beta equals to 180 degrees. Therefore, we substitute 2 alpha plus 2 beta in this equation by 180 degrees. So it is 180 degrees plus x plus y equals to 360 degrees. Here we will subtract 180 degrees from this equation, and we will get that x plus y equals to 360 degrees minus 180 degrees is 180 degrees. So in total we should find out that x plus y equals to 180 degrees. In the next step, I will present to you rule 30, and we will implement rule 30 in our drawing. According to rule 30, set angles that subtend on equal chords or equal arcs are equal to each other. Repeat again, according to rule 30, set angles that subtend on equal chords or equal to each other. So in the drawing we have a circle. This is set angle COD that is equals to alpha degrees in its size, and the subtend on chord CD. Again, set angle COD subtend on chord CD. Likewise, we have another set angle that is set angle AOB that is equals to beta degrees in its size, and the subtend on chord AB. According to this rule 30, if chord AB equals to chord CD, that is to say, if those two set angles subtend on equal chords, then they must be equal to each other in their sizes. That is to say, alpha equals to beta. But again, according to rule 30, if two or more set angles subtend on equal chords, they must be equal to each other in their sizes. So you can actually implement rule 30 in our drawing. So I'll copy this circle in a new page, and I'll copy also this triangle AOB in the new circle, and then I will do a construction, and then we'll implement all 30 in the new drawing. So first of all, I will copy this circle in a new page. So I copied the original circle to this new page, and this is center angle AOB. This is equals to y decreased in its size, and center angle AOB subset of code AB. This is equals to 8 units in its length according to what is given as the question. So in the next step, we'll do a construction. That is to say, from this point B, we'll draw a chord that is equals to 6 units in its length according to our construction. And repeat again, from point B, we will draw a chord that is equals to 6 units in its length according to our construction. So actually, we constructed chord BC that is equals to 6 units in its length according to our construction. In the next step, we will join points O and C together by straight line. By doing this construction, we can do center angle BOC. This is center angle BOC, that's subset of chord BC, that equals to 6 units in its length. Now we can implement all 30 in our drawing. Why? Because in the original drawing, we have center angle POQ, that equals to x degrees in its size, and the subset of chord PQ, that is equals to 6 units in its length. And because of the fact that those two center angles are both subset on equal chords, chord PQ equals to 6 and chord BC equals to 6 also. So those two center angles, they are both subset on equal chords, and therefore they must be equal to each other in their sizes. But the size of this center angle POQ is x, therefore the size of this center angle BOC must be also equal to x degrees in its size. According to Rule 30, that says that center angles that subtend on equal course are equal to each other in their sizes. Okay, repeat again. Those two center angles, they subtend on equal course, that is equal to 6 units in itself, and therefore they must be equal to each other in their sizes. But the size of this center angle P or Q is x, therefore the size of this center angle BOC must be also equal to x degrees in its size, according to Rule 30. So by doing this construction, we create that the big angle, angle AOC. Angle AOC equals to x plus y degrees in its size. But we have already found out that x plus y equals to 180 degrees. Therefore, the big angle AOC is equals to x plus y. It is actually equals to 180 degrees in its size. And we know that any angle that is equal to 180 degrees in its size, it is defined as a straight line. So AC is a straight line. So write it down. AC is a straight line. But AC is a straight line that touches the circle at 2 points, A and C. And therefore AC is a chord. AC is a chord that passes through point O, that is the center of the circle. And we know that any chord that passes through the center of the circle must be the diameter of the circle. Therefore, chord AC that passes through point O, that is the center of the circle, must be the diameter of the circle. So I want to know if we found out that chord AC is the diameter of the circle, because it passes through point O, that is the center of the circle. Here we can implement Rule 7. According to Rule 7, if a peripheral angle subtends on the diameter of the circle, then it is equal to 90 degrees in its size. In the drawing, we have a circle. This is peripheral angle ACB that subtends on chord AB, that is the diameter of this circle. And therefore, according to this rule 7, peripheral angle ACB must be equal to 90 degrees in its size because it subtends on the diameter of the circle. We can definitely implement Rule 7 in our drawing. Why? Because in our drawing, we have peripheral angle ABC that subtends on chord AC, that is the diameter of the circle. Therefore, according to Rule 7, peripheral angle ABC must be equal to 90 degrees in its size. So in the next step, I'll copy the triangle ABC in a new page, and we will implement the Pythagoras theorem on this right triangle, triangle ABC. The diameter AC equals to it is twice as long as the radius. If the radius is R, then the diameter AC must be equal to 2R. Side AB equals to 8 units in itself, and side BC equals to 6 units in itself. Here by PT is the abbreviation for Pythagoras theorem. So actually, this is the right triangle ABC that according to the Norway, it is the right triangle ABC. AC squared, that is the square of the hypotenuse, equals to AB squared plus BC squared. So already now, AC squared, that is the square of the hypotenuse, equals to AB squared plus BC squared. The hypotenuse AC equals to 2r, therefore AC squared is 2r squared, that is 4r squared. And it is equals to AB squared. AB is 8, therefore AB squared is 8 squared, that is 64. Plus BC squared. BC is 6, therefore BC squared is 6 squared, that is 36. 64 plus 36 is 100. So in total we found out that 4r squared equals to 100. Here we will divide this equation by 4 and we get that r squared equals to 100 over 4 is 25. So r squared equals to 25. Here we take a root out of this equation. And we get that the radius r equals to the square root of 25, that is 5. So if you found out that the radius r of this circle is equal to 5 units in its length. Our test is to find out the area of this circle. So actually we know that the area of any circle equals to pi times the radius of the circle squared. Okay, again, the area of any circle equals to pi times the radius of the circle squared. And therefore, the area of any circle must be equal to pi times the radius of our circle squared. The radius of our circle squared is r squared. So the area of our circle must be equal to pi r squared, which is pi times r squared. R is 5, therefore r squared is 5 squared, that is 25. So in total we should find out that the area that we are looking for in this question, that is the area of this circle, is equal to either 25 pi square units in its size. In terms of numbers, the area of this circle is equal to 78.54 square units in its size. And again, if we found out that the area of this circle, it is equal to either 25 pi square units in its size, or in terms of numbers, the area of this circle equals to 78.54 square units in its size. So we finish with the first method. In the next step, I will present to you how to find out the area of this circle according to the second method. In the second method, we use with some of the things that we already found out in the first method. So in the first method, we have already found out that those two angles are both equal to alpha. Both those two angles are both equal to 90 degrees. So we have the right triangle AMB. In the right triangle AMB, this angle equals to alpha, this angle equals to 90 degrees, and therefore this third angle must be equal to 90 degrees minus alpha. Why? Because 90 degrees minus alpha plus alpha is 90 degrees, and 90 degrees plus 90 degrees, it is equal to 180 degrees. That is the sum of the angles in any triangle. Likewise, in the right triangle PMQ, this angle equals to alpha, this angle equals to 90 degrees, and therefore this perpendicular angle must be equal to 90 degrees minus alpha, according to the same rule that the sum of the angles in any triangle is equal to 180 degrees. It is very easy to see that those two right angles are similar to each other according to angle similarity rule. So we'll explain anyway why those two right angles are similar to each other. First of all, those two angles are both equal to alpha, therefore they are equal to each other. In addition, those two angles are both equal to 90 degrees, and therefore they are equal to each other. And finally, those two angles are both equal to 90 degrees minus alpha, and therefore they are equal to each other. So I actually prove that all the figures of this big right triangle A and B correspond equal to all the figures of this small right triangle P and Q. And therefore, those two right triangles are similar to each other according to angle similarity rule. So I write it down. I should found that the big right triangle A and B is similar. This is the sign of similar to the small right triangle PMQ according to angle similarity rule. And from the fact that those two right angles are similar to each other, we will derive that the following relationship exists between their sides. We derive that side AB of the right triangle A and B over side PQ of the right small triangle PMQ is equal to side AM of the right triangle A and B over side PM of the right triangle PMQ, and it is also equal to side MB of the right triangle AMB over side MQ of the right triangle PMQ. Repeat again, from the fact that those two right triangles are similar to each other, we will derive that the following relationship exists between their sides. We will derive that side AB of the right triangle AMB over side PQ of the right triangle PMQ is equal to side AM of the right triangle AMB over side PM of the right triangle PMQ, and it is also equal to side MB of the right triangle AMB over side PQ over side MQ of the right triangle PMQ. AB is 8, over PQ is 6, and it is equal to AM over PM. So 8 over 6 equals to AM over PM. Here we will divide this number, both the numerator and the denominator of this number, by 2, and we get that 8 over 2 is 4, and 6 over 2 is 3. So 3 first equals to AM over PM. Here we will multiply both the numerator and the denominator of this number by A. You get it 3A, 4A over 3A equals to AM over PM. A over A is 1. And it is allowable to multiply any field by 1. By multiplying any expression by 1, you will not change the value of the expression. So the operation is allowable. What is the meaning of this equation? The meaning of this equation is that if AM equals to 4A, then PM must be equal to 3A. So we can write down now all you're knowing that if AM equals to 4A, then PM must be equal to 3A, according to our equation. From this equation, we will derive that AB over PQ equals to MB over MQ. AB over PQ is 4 firsts, so 4 firsts equals to MB over MQ. Here we will multiply both the numerator and the denominator of this number by B, and we get that 4B over 3B equals to MB over MQ. What is the meaning of this equation? The meaning of this equation is that if MB equals to 4B, then MQ must be equal to 3B. So, I'll write it down in our equation drawing. According to this equation, we found out that if MB equals to 4B, then MQ must be equal to 3B. PB is a chord in this circle. PB is a chord, it is absolutely a straight line. So if you focus on the right side of the straight line, PB and point M here, the sum of the angles must be equal to 180 degrees according to rule 3. Rule 3 states that the sum of the angles on one side of the straight line is equal to 180 degrees. So which angles we have the right side of the straight line PB at point M, we have this angle that is right angle, plus this missing angle, the sum of those two angles must be equal to 180 degrees according to rule 3. Therefore, this missing angle must be equal to 90 degrees in its size. In the next step, we join points B and Q together by a straight line. By joining points B and Q, we get the right triangle, triangle MBQ. So it could be the right triangle MBQ in a new page, and implement the Pythagoras theorem on this right triangle MBQ. Here by PT is the operation for Padana storing. So actually, this is the right triangle MBQ that are coming from the original drawing. This right triangle MBQ, according to the Pythagoras theorem, BQ squared, that is the square of the hypotenuse, equals to MB squared plus MQ squared. So I write it down. BQ squared, that is the square of the hypotenuse, must be equal to BM squared plus QM squared. BQ is the missing side, so we limit it, so it is BQ squared equals to BM squared. BM is 4B, therefore BM squared is 4B squared, that is 16B squared, plus QM squared. QM is 3B, therefore QM squared is 3B squared, that is 9B squared. 16B squared plus 9B squared is 25B squared. So in total we should find out that BQ squared equals to 25B squared. Here we take out of this equation and we get that the missing side BQ is equal to the square root of 25, that is 5, times square root of B squared, that is B. So in total we should find out that the missing side BQ is equal to 5B units in its length. This is the missing side BQ that equals to 5B units in its length. In the next step, we will calculate the area of this triangle ABQ using two different methods. And then we create an equation that says that the area of triangle ABQ according to the first method must be equal to the area of triangle ABQ according to the second method. So in the first method, we calculate the area of triangle ABQ according to the rule that the area of any triangle equals to the base of the triangle times the height to the base over 2. So the area of triangle ABQ equals to the base, that is AQ, we'll choose the base as AQ, times the height to the base, that is MB. Why MB is the height to the base? Because it creates 90 degrees with the base AQ. So this times MB, the height to the base is MB divided by 2. So according to the first method, the area of triangle ABQ is equal to the base AQ times the height to the base, that is MB, divided by 2. And it must be equal to the area of triangle ABQ according to the second method. In the second method, we use a new formula in order to find out the area of this triangle ABQ. According to the new formula, we have in the drawing triangle ABC that could be any triangle. side AB of this triangle ABC equals to A units in its length, side AC equals to B units in its length, and side BC equals to C units in its length. This is angle BAC, this is equals to theta degrees in its size. So in this triangle ABC, the area of this triangle ABC equals to A times B times sinus theta over 2. Again, the area of this triangle ABC that could be any triangle is equal to A times B times sinus theta over 2. That is to say, the area of any triangle equals to the multiplication of the two sides by each other times sinus the angle between those two sides, that is sinus theta over 2. We use the new formula in order to find out the area of this triangle ABQ. So according to the second method, the area of this triangle ABQ will be equal to AB times BQ, that is the multiplication of the two sides by each other, times sinus the angle between those two sides. What is the angle between those two sides AB and BQ? It is angle ABQ. So it is times sinus angle ABQ divided by 2. Repeat again, according to the second method, the area of this angle ABQ equals to AB times BQ, that is the multiplication of two sides by each other, times sinus the angle between those two sides AB and BQ. The angle between those two sides AB and BQ is angle ABQ. So it is times sinus angle ABQ over 2. So the area of triangle ABQ according to the first method must be equal to the area of triangle ABQ according to the second method. So we have 2 on both sides of this equation, so 2 will get cancelled. In the next step, we'll find out what is the value of sinus angle ABQ. I use the law of sines in order to find out the value of sinus angle ABQ. The law of sines is true in any triangle. This is a triangle ABC that could be any triangle. Side AB of the triangle ABC equals to C units in its length. Side AC equals to B units in its length. This is side BC, this equals to A units in its length. This is angle alpha, this is angle beta, and this is angle gamma. According to the law of sines, the following equation is true. That A over sinus alpha equals to B over sinus beta equals to C over sinus gamma equals to 2R. And 2R is the diameter of the circle that blocks this triangle ABC. Again, 2R is the diameter of the circle that blocks this triangle ABC. So we can implement full the law of sines in our drawing. Because of the fact that triangle ABC could be any triangle, you can implement the law of sines, this triangle ABQ. According to the law of sines, the following equation will be true. AQ over sinus angle ABQ equals to 2R. Again, AQ over sinus angle ABQ equals to 2R. And 2R is the diameter of this circle that blocks triangle ABQ. So, write it down. According to the law of sines, in our original drawing, the following equation will be true. AQ over sinus angle ABQ equals to 2R. This equation is the implementation of the law of sines in our drawing. Here we will multiply this equation by sinus angle ABQ, and then we will divide it simultaneously by 2R. This way we get that sinus angle ABQ is equal to AQ over 2R. Now we can substitute sinus angle ABQ in this equation by AQ over 2R. We do it now and we get that AQ times MB equals to AB times BQ and sinus angle ABQ is AQ over 2R. Again, sinus angle ABQ is AQ over 2R. So we substitute sinus angle ABQ by AQ over 2R. And we get that AQ times MB equals to AB times BQ times AQ over 2R. We have AQ on both sides of this equation, so AQ will get cancelled. After we cancel AQ on this side of the equation, we left only with MB equals to AB times BQ over 2R. So today we should find out that MB equals to AB times BQ over 2R. Here we will multiply this equation by R and then we will divide it by MB simultaneously in order to find out the value of R, that is the radius of this circle. That's it. It's area that we are looking for. Repeat again, we will multiply this equation by R, then we will divide it by MB. And we get that R equals to AB times BQ over 2 times MB. Repeat again. In total we should find out that the radius of this circle, that is area that we are looking for this question, is equals to AB times BQ over 2 times MB. So R equals to AB is 8 according to what is given in the question, times BQ is 5B. Over 2 times MB is 4B. So in total we should find out that R, that is the radius of the circle, equals to 8 times 5B over 2 times 4 times B. We have B in the numerator and B in the denominator, so B will get cancelled. We have 8 in the numerator and 2 times 4, that is 8 in the denominator. So these two numbers, these numbers will also get cancelled, and we left only with 5. So if we found out that the radius of this circle R equals to 5 units in its length. Our test is to find out the area of this circle. Actually, we know that the area of any circle equals to pi times the radius of the circle squared. Repeat again, the area of any circle is equal to pi times the radius of the circle squared. Therefore, the area of our circle must be equal to pi times the radius of our circle squared. So it is pi times the radius of our circle squared. The radius of our circle squared is r squared. So in total, the area of our circle must be equal to pi r squared. So it is pi times r squared. R is 5, therefore r squared is pi squared, that is 25. So in both methods, we have found out that the area of this circle, that is the area that we are looking for in this question, is equal to either 25 pi square units in its size, or in terms of numbers, it is equal to 78.54 square units in its size. So we finish with the second method of the second question. In the next step, on some of the lecture, we'll start with the first question, of course. Our task in the first question is to find out the area of this big rectangle EFQH. So in the Roman rectangle EFQH, the big rectangle EFQH, inside this big rectangle we have 3 circles. The radius of this small circle equals to 5 units in its length. The radius of this medium circle equals to 6 units in its length. And the radius of this big circle equals to 8 units in its length. Again, our task is to find out the area of this big rectangle EFQH. So first of all, we know that the angles, all the angles in a rectangle are right angles. So those 4 angles are all right angles. In the next step, we implemented rule 1 in our drawing. According to rule 1, a tangent to a circle is perpendicular to the radius drawn to its point of tendency. So in the drawing we have a circle. This is tangent AB, this is tangent to this circle at point M. We have the radius OM that is equals to R. The radius OM is drawn to point M, that is the point of tendency of tangent AB with this circle. And whenever you have radius that is drawn to the point of tendency, then tangent AB will be perpendicular to the radius MO. If AB is perpendicular to MO, it means this angle equals to 90 degrees, and this angle equals to 90 degrees according to this rule, rule 1. We implemented rule 1 a lot of times in our drawings. So I explain only the implementation of rule 1 in one case, and then in the other cases we implement rule 1 immediately without any explanation, in order to save time. So I take, for example, the medium circle, the radius QB equals to 6 units in its length. The radius QB is drawn to point B, that is the point of tendency of tangent HQ with this medium circle. And whenever you have radius that is drawn to the point of tendency, then tangent HQ will be perpendicular to the radius BQ. If HQ is perpendicular to BQ, it means that this angle equals to 90 degrees, and this angle also equals to 90 degrees according to rule 1. Likewise, we implemented rule 1 here. According to rule 1, this angle equals to 90 degrees, and this angle also equals to 90 degrees. And we implemented rule 1 also here. This angle equals to 90 degrees, and this angle equals to 90 degrees. And we extended we joined points S and M together by a straight line. SL is of course the radius of this big circle that is equals to 8 units in incident. According to rule 1, this angle equals to 90 degrees and this angle equals to 90 degrees. And we define the point of tendency of tangent EQ with this small, big circle. This point is point T, and we join points S and T together by a straight line. ST is of course the radius of this big circle is equals to 8 units. According to rule 1, this angle equals to 90 degrees and this angle also equals to 90 degrees. So in the upper small quadrangle CFTS, we have 1, 2, 3 rectangles, and therefore this 4 angle must be equal to 90 degrees in its size. And therefore quadrangle CFTS is a rectangle, and you know that the opposite sides of a rectangle are equal to each other. So in the small rectangle CFTS, side ST must be equal to the opposite side CF. But ST is 8, therefore the opposite side CF must be also equal to 8 units in its length. Likewise, we have in the lower quadrangle STQL, we have 1, 2, 3 rectangles, and therefore this 4th angle must be equal to 90 degrees in its size. So if you found out the big angle CSL is equal to 90 degrees plus 90 degrees, that is 180 degrees. Therefore, we know that any angle that is equal to 180 degrees in its size, it is defined as a straight line. Therefore, CL is a straight line. And because of the fact that CL is a straight line, it means that in this shape ECLH, we have 1, 2, 3, 4 4 sides. And therefore, shape ECLH is a quadrilateral. Shape ECLH is a quadrilateral with 4 right angles. 1, 2, 3, 4. And therefore, quadrilateral ECLH is a rectangle because it has 4 right angles. But we also know that the opposite sides of a rectangle are equal to each other. So in the big rectangle ECLH, side TL must be equal to the opposite side EH. But CL equals to 8 plus 8, that is 16. Therefore, the opposite side EH must be also equal to 16 units in its length. So if you found out that the width of this big rectangle EFQH, the width EH equals to 16, the only thing that is left to find is to find the length of the rectangle that is area that we are looking for in this question. That is to say, we have to find out the value of the length EF. So in the next step, we extended the radius BQ by a straight line until it touches side EF of the rectangle. We define the touching point of the extended radius BQ with side EF. This point is point M. By doing this construction, we granted quadrangle EMBH. Inside this quadrangle EMBH, we have 1, 2, 3 angles. Therefore, this 4th angle must be equal to 90 degrees in its size. And therefore, quadrangle EMBH is a rectangle. And we know that the opposite sides of a rectangle are equal to each other. When rectangle EMBH, side EH must be equal to the opposite side MB. But EH is 16, therefore the opposite side MB must be also equal to 16 units in its length, if MB equals to 16. Likewise, we have quadrangle MCLB. Inside quadrangle MCLB, we have 1, 2, 3 rectangles. Therefore, this 4th angle must be equal to 90 degrees in its size. So, those two quadrilaterals, they are both rectangles. In the next step, we did another construction. That is to say, from point P, that is the center of this small circle, we do perpendicular on MB. Again, from point P, we do perpendicular on MB. So this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. We define the touching point of the perpendicular from point P and MB. This point is point K. By doing this construction, we get the quadrilateral AMKP. Inside quadrilateral AMKP, we have 1, 2, 3 rectangles, and therefore this fourth missing angle must be also equal to 90 degrees in its size, and therefore quadrilateral AMKP is a rectangle because it has 4 rectangles. But we also know that the opposite sides of a rectangle are equal to each other. So in the small rectangle AMKP side, AP must be equal to the opposite side MK, but AP is 5, therefore the opposite side MK must be also equal to 5 units in its length. So what is the length of this missing line segment KQ? KQ equals to MB, that is 16, minus MK, that is 5. 16 minus 5 is 11, minus QB, that is 6. 11 minus 6 is 5. So KQ equals to 5 units in its length. In the next step, we join points P and Q together by straight line. Point P is the center of the small circle. Point Q is the center of this medium circle. Therefore, PQ is the distance between the centers of those two circles. That is to say, PQ is the straight line that connects the centers together. And according to rule 10, the straight line PQ that connects the centers of those two circles together must pass through the attaching point, that is point O. Or POQ is one straight line. Again, POQ is one straight line according to rule 10. It is very clear that those two circles have an external length between them at point O, and therefore whenever we have an external length between those two circles like here, we can implement rule 10. So according to rule 10, POQ is one straight line. If POQ is one straight line, it means that PQ must be equal to PO, that is 5, plus OQ, that is 6. So PQ equals to 5 plus 6, that is 11. PQ is 11, and KQ is 5. The only missing side we have here is the side PK. So in the next step, I copy the right triangle PKQ in the new page, the right hand triangle PKQ in the new page, and we implemented the bottom stone with this right triangle PKQ. According to the quadrilateral stone, in any right triangle, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. This is the right triangle PKQ that is coming from the original drawing. In this right triangle PKQ, according to the quadrilateral stone, PQ square, that is the square of the hypotenuse, equals to PK square plus KQ square. PQ is 11, therefore PQ square is 11 square, that is 121, and this is equals to PK square. PK is the missing side, so it is PK square plus KQ square. KQ is 5, therefore KQ square is 5 square, that is 25. So in total, we found out that 121 equals to PK square plus 25. Here we subtracted 25 from this equation, and finally found out that 121 minus 25 is 96. So 96 equals to PK square. 96 is 16 times 6, so 96 times 16 times 6. So 16 times 6 equals to PK square. Here we took a root out of this equation, and finally found out that PK, the missing side PK, equals to the square root of 16, that is 4. Inside the root we left only with 6. So in total PK equals to 4 times root of 6 units in its length. This is the missing side PK, this equals to 4 times root of 6 units in its length. We already found out that AMKP is a rectangle, and we know that the opposite sides of a rectangle are equal to each other. So in the small rectangle AMKP, side PK must be equal to the opposite side AM. But PK is 4 times root of 6. Therefore, the opposite side AM must be also equal to 4 times root of 6 units in its length. In the next step, we join the center of this circle, that is point Q, the center of the medium circle, with the center of this big circle, that is S. So we join the two centers together. So QS is the straight line that connects the centers of the medium circle with the center of the big circle. According to rule 10, it is clear that those two circles have an acceleration between them at point Y. So we can implement rule 10. According to rule 10, the straight line that connects the centers together, that is the straight line QS, must pass through point Y, that is their touching point. Again, the straight line QS must pass through their touching point, that is point Y. Or QYS is one straight line. QYS is one straight line. If QYS is one straight line, it means that QS must be equal to QY, that is 6, plus YS, that is 8. So QS in total equals to 6 plus 8, that is 14. In the next step, from point Q, that is the center of this medium circle, we do perpendicular on CL. Again, from point Q, we do perpendicular on CL. So this angle equals to 90 degrees, and this angle also equals to 90 degrees, according to our construction. We define the touching point of the perpendicular from point Q and CL. This point is point J. By doing this construction, we can deduct quadrilateral QSLB. Inside quadrilateral QSLB, we have 1, 2, 3 rectangles, and therefore this fourth rectangle must be equal to 90 degrees in its size, and therefore quadrilateral QSLB is a rectangle. But we also know that the opposite sides of a rectangle are equal to each other. So in rectangle QSLB, side QB must be equal to the opposite side JL. But QB is 6, therefore the opposite side JL must also equal to 6 units in its length. What is the length of this short line segment SJ? SJ equals to SL, that is 8, plus JL, that is 6. So in total, SJ equals to 8 minus 6, that is 2. In the next step, I copied this green right triangle QSJ in a new page, and we implemented the pattern storm on this right green triangle QSJ. The hypotenuse QS is 14, SJ is 2, and the missing side is QJ. So this is the right triangle QSJ that are going from the original drawing. In this right triangle QSJ, QS squared, that is the square of the hypotenuse, equals to SJ squared plus QJ squared. QS is 14, therefore QS squared is 14 squared, that is 196. And it is equals to SJ squared. SJ is 2, therefore SJ squared is 2 squared, that is 4, plus QJ squared. QJ is the missing side, so we need to see this, so it is plus QJ squared. So total we found out that 196 equals to 4 plus QJ squared. Here we subtracted 4 from this equation, and finally found out that 196 times 4 is 192 equals to QJ squared. We substituted 192 by 64 times 3, and this equals to QJ squared. We took a root out of this equation, and finally found out that QJ, the missing side QJ, equals to the square root of 64, that is 8. So inside the root we left only with 3. So in total QJ equals to 8 times square root of 3 units in its length. This is the missing side QJ, that is equals to 8 times square root of 3 units in its length. This is quadrilateral MQJC. Inside quadrilateral MQJC, we have 1, 2, 3 right angles, and therefore this missing angle must be also equal to 90 degrees in its size. Therefore, quadrilateral MCJQ is a rectangle because it has 4 right angles. But we also know that the opposite sides of a rectangle are equal to each other. So in rectangle MCJQ, side QJ must be equal to the opposite side MC. But QJ is 8 times square root of 3, therefore the opposite side MC must be equal to also to 8 times square root of 3 units in its length. Our task is to find out the area of this big rectangle EFQH. There are funny octagon equals to the width of the octagon times the length. The width of this big octagon EFQH is E edge and the length is EF. Okay, again. The width is E edge and the length is EF. E edge, the width E edge equals to 16 and the length EF equals to EA plus AM plus MC plus CF. Repeat again. The width EF equals to 16 and the length EF equals to EA plus AM plus MC plus CF. So there, the big octagon EFQH equals to the width that is 16 times EA is 5 plus AM is 4 times square root of 6 plus MC that is 8 times square root of 3 plus CF that is 8. So in total, there the big octagon EFQH equals to 16 times 5 plus 4 times square root of 6 plus 8 times square root of 3 plus 8. The value of this expression in total it is equals to 586.47 square units in its size. So the answer to the first question is that the area of this big rectangle EFQH, that is the area that we are looking for in this question, it is equals to 586.47 square units in its size. So we finish with the first question. In the next step I presented to the second question of this lecture and answer for the second question by using two different methods. In the second question, our task is to find out the area of this circle. In the drawing we have a circle. This is called AB, this is equals to 8 units in its length. This is called PQ, this is equals to 6 units in its length. This is again PMQ, that is the right angle. Again, our task is to find out the area of this circle. So first of all, I presented to you Rule 29 and we implement Rule 29 in our drawing. According to Rule 29, wave angles that subtend on the same arc are equal to each other in their sizes. In the drawing we have a circle. This is wave angle BDC that equals to alpha degrees in size, and wave angle BDC subtend on arc BC. Likewise, we have another wave angle. This is wave angle BEC is equals to beta degrees in size and is subtend on the same arc BC. And because of the fact that those two angles they are both subtend on the same arc BC, they must be equal to each other in their sizes. That is to say, alpha equals to beta. We can implement Rule 29 in our drawing. I put in our drawing, we have wave angle BAQ that subtend on arc BQ. Likewise, we have another wave angle, that is wave angle QPB, that is also subtend on the same arc BQ. And because of the fact that those two wave angles subtend on the same arc, that is arc BQ, they must be equal to each other in their sizes. So if the size of this wave angle BAQ is alpha, then the size of this wave angle QPB must be also equal to alpha because they are equal to each other according to Rule 29. Because they subtend on the same arc BQ. Likewise, if we focus on this arc RKP, we have wave angle PQA that subtend on RKP. Likewise, we have another wave angle PBA that is also subtend on the same arc RKP. And because of the fact that those two wave angles subtend on the same arc RKP, they must be equal to each other and their sizes. So the size of this wave angle PQA is equals to beta, then the size of this wave angle PBA must be also equal to beta because they are equal to each other according to Rule 29. In the next step, I presented to you Rule 13 and we implemented Rule 13 in our drawing. according to rule 13, a center angle is twice as large as the peripheral angle subtended on the same chord or the same arc. So in the drawing we have a circle. This is peripheral angle ACB that subtend on arc AB or chord AB, doesn't matter. Likewise, we have center angle AOB that subtend on the same arc AB. And because of the fact that peripheral angle ACB subtend on arc AB and it is equal to theta degrees in size, therefore the center angle AOB that subtend on the same arc AB must be twice as big as this peripheral angle ACB that subtend on the same arc AB. The size of this peripheral angle ACB is theta, therefore the size of the peripheral angle must be equal to 2 theta. So we can implement rule 13 in our drawing. In our drawing, we graded center angle AOP that subtend on arc AP. We have peripheral angle AQP that is also subtend on the same arc AP, and according to rule 13, the size of the center angle AOP must be twice as big as this peripheral angle AQP that subtend on the same arc AP. The size of peripheral angle AQP is better, therefore the size of the center angle AOP that subtend on the same arc AB must be equal to 2 beta. Likewise, we have center angle BOQ that subtend on arc BQ. But we also have peripheral angle BAQ that subtend on the same arc BQ. According to rule 13, the size of this center angle BOQ must be twice as big as the size of this peripheral angle BAQ that subtend on the same arc BQ. The size of this peripheral angle BAQ is alpha, therefore the size of this center angle BOQ that subtend on the same arc BQ must be equal to alpha. In the next step, according to rule 13 of course, in the next step we define this angle, center angle POQ as x, and we define this center angle AOB as y. And we have the rule that says that the sum of the angles around any point is equal to 360 degrees. Okay, the sum of the angles around any point is equal to 360 degrees. So the sum of the angles around point O, that is the center of the circle, must be equal to 360 degrees. So in case we have around point O, we have 2 alpha plus 2 beta plus x plus y. In total, the sum of those 4 angles must be equal to 360 degrees. And again, if we focus on point O, that is the center of the circle, the sum of the angles around point O must be equal to 360 degrees. So 2 alpha plus 2 beta plus x plus y, in total must be equal to 360 degrees. But we only found out that 2 alpha plus 2 beta equals to 180 degrees. So we can substitute 2 alpha plus 2 beta by 180 degrees. We did it and we found out that 180 degrees plus x plus y equals to 360 degrees. Here we subtracted 180 degrees from this equation, and we found out that x plus y equals to 360 degrees minus 180 degrees and 180 degrees. So in total we found out that x plus y equals to 180 degrees. In the next step, I presented to you rule 30, and we presented rule 30 in our drawing. According to rule 30, center angles that subtend on equal chords are equal to each other. In the drawing we have second, this is center angle COD that subtend on chord CD. This is center angle EOB that subtend on chord AB. According to this rule 30, if chord AB equals to chord CD, then those two center angles must be also equal to each other in their sizes. That is to say, alpha equals to beta. So if 2 or more center angles subtend on equal arcs, they must be also equal to each other in their sizes. We can implement rule 30 in our drawing. First of all, I copied this circle to a new page, and I also copied this center angle AOP this is equal to y degrees in size, and chord AB, this is equal to 8 units in its length. So this is the circle that I copied from the original drawing. This is center angle AOB, that I also copied from the original drawing. The size of center AOB is y degrees, and its offset on chord AB is equal to 8 units in its length. In the next step, we did the construction, that is to say from point B, I draw a chord BC, that is equal to 6 units in its length. Repeat again, from point B, I draw chord BC, that is equal to 6 units in its length, according to my construction, chord BC equals to 6 units in its length. And then I join points O and C together by a straight line. By doing this construction, get there, set angle BOC, that subtend on chord BC, and chord BC equals to 6 units in its length. Now we can implement rule 30 in our drawing. Because in our drawing, we have in the original drawing center angle POQ, that is equal to x degrees in size, and its subtend on chord PQ, that is equal to 6 units in its length. And because of the fact that those two center angles subtend on equal chords, chord PQ equals to 6, and chord BC also equals to 6. So those two center angles, they are both subtend on equal chords. Therefore, according to rule 30, they must be equal to each other and their sizes. The size of this center angle QOP is x. Therefore, the size of this center angle BOC must be also equal to x. So, in the drawing, we have the big angle AOC equals to x plus y degrees. But we have already found out that x plus y equals to 180 degrees. That is to say, the big angle AOC equals to 180 degrees in size. And we know that any angle that is equal to 180 degrees in its size, it is defined as a straight line. Therefore, AC is a straight line. But AC is a straight line that touches the circle at 2 points, A and C. Therefore, AC is a chord that passes through point O, that is the center of the circle, and we know that any chord that passes through the center of the circle must be the diameter of the circle. Therefore, chord AC is the diameter of this circle. Here we implemented rule 7. According to rule 7, if a peripheral angle subtend on the diameter of the circle is equal to 90 degrees in its size. And the drawing in a circle, this is peripheral angle ACB, that subtend on a chord AB, that is the diameter of the circle, and therefore according to this rule 7, is equal to 90 degrees in its size. So we can implement rule 7 in our drawing. Because in our drawing, we have center angle, peripheral angle ABC, that subtend on chord AC, that is the diameter of the circle. Therefore, according to rule 7, peripheral angle ABC must be equal to 90 degrees in size. The next step, I copied the right triangle ABC in the new page and we implemented the Pythagoras theorem in this right triangle ABC. Side AB equals to 8, side BC equals to 6 according to our construction, and AC is the diameter of the circle. If the radius is out, then the diameter is 12. So, this is the right triangle ABC, that is coming from the original drawing. In this right triangle ABC, according to the Pythagoras theorem, AC squared, that is the square of the hypotenuse, equals to AB squared plus BC squared. AC is 12, therefore AC squared is 4 squared, that is 4 squared, and it is equal to AB squared. AB is 8, therefore AB squared is 8 squared, that is 64, plus BC squared. BC is 6, therefore BC squared is 6 squared, that is 36. So in total, 4R squared equals to 64 plus 36, that is 100. So 4R squared equals to 100. We divided this equation by 4 and found out that R squared equals to 100 over 4, that is 25. We took a root to R squared equals to 25, we took a root of this equation and found out that the radius R of this circle is equal to the square root of 25, that is 5. Our test is to find out the area of this circle. Actually, we know that the area of any circle equals to pi times the radius of the circle squared, and therefore the area of our circle must be equal to pi times the radius of our circle squared. The radius of our circle squared is R squared, so Therefore, 1 second must be equal to pi r squared. But r is 5, therefore r squared is 5 squared, that is 25. So if you found out that the area of this secant is equal to either 25 pi square units in size, or there are some numbers, the area of this secant equals to 78.54 square units in size. We finish with the first method. In the next step, I present to you how to find out the area of this secant according to the second method. In the second method, we use some of the things that we already found out in the first method. In the first method, we already found out that those two angles are both equal to alpha, and those two angles are both right angles. So we use it in this second method. So in the drawing, we have the right triangle A and B. In the right triangle A and B, this angle equals to alpha, this angle equals to 90 degrees, and therefore this missing angle must be equal to 90 degrees minus alpha. Why? Because 90 degrees minus alpha plus alpha is 90 degrees, and 90 degrees plus 90 degrees is equal to 180 degrees. That is the sum of the angles in any triangle. Likewise, in this right triangle PMQ, this angle equals to alpha, this angle equals to 90 degrees, and therefore this angle must be equal to 90 degrees minus alpha, according to the sum rule that the sum of the angles in any triangle is equal to 180 degrees. Those two triangles are similar to each other according to angle similar to. That is to say, those two angles are both equal to alpha, therefore they are equal to each other. In addition, those two angles are both equal to 90 degrees, and therefore they are equal to each other. And finally, those two angles are both equal to 90 degrees minus alpha, therefore they are equal to each other. So if you found out that all the triangles of this right triangle A and B are corresponding equal to all the triangles of the right triangle P and Q, and therefore those two right triangles are similar to each other according to angle similar to. And again, if you found out that the right big triangle A and B is similar to the right triangle P and Q according to angle similar to. And from the fact that those two right triangles are similar to each other, we will derive that the following relationship exists between their sides. We derive that side A and B of the right triangle A and B, or side PQ of the right triangle PMQ is equal to side AM of the right triangle A and B, or side PM of the right triangle PMQ, and it is also equal to side AB of the right triangle A and B, or side MQ of the right triangle AMQ, PMQ. And we derive that AB over PQ equals to AM over PM equals to AM over MQ. AB is 8, PQ is 6, so 8 over 6 equals to AM over PM. We divided both the numerator and the denominator of this number by 2, 8 over 2 is 4 and 6 over 2 is 3, so 4 thirds equals to AM over PM. We multiplied both the numerator and the denominator of this number by A, and found out that 4A equals to 4A over 3A equals to AM over PM. This equation means that if AM equals to 4A, then PM equals to 3A. Again, if AM equals to 4A, then PM equals to 3A. Those two sides of the equation are also equal to each other. AB over PQ is 4 firsts, so 4 firsts equals to MB over MQ. Again, 4 firsts equals to MB over MQ. We multiply both the numerator and the denominator of this number by B, and finally found out that 4B over 3B equals to MB over MQ. This equation means that if MB equals to 4B, then MQ must be equal to 3B. Repeat again. If MB equals to 4B, then MQ must be equal to 3B. PB is a chord, so PB is a chord, it is absolutely a straight line. So if you focus on the right side of the straight line PB at point M, here the sum of the angles must be equal to 180 degrees according to all three. All three says that the sum of the angles from one side of the straight line is equal to 180 degrees. So which angles we have at the right side of PB at point M? We have this angle that is 90 degrees, plus this missing angle. In total, the sum of those two angles must be equal to 180 degrees according to all three. Therefore, this missing angle must be equal to 90 degrees in its size. In the next step, we join points B and Q together by straight line. By joining points B and Q and straight line, you created here the right triangle BMQ. In the next step, we'll copy the right triangle BMQ in a new page, and we implement it to this right triangle BMQ the Pythagoras theorem. This is the right triangle BMQ that evolved from the original domain. In this right triangle BMQ, BQ squared, that is the square of the hypotenuse, equals to BM squared plus MQ squared. BQ is the missing side, so it is. So it is BQ squared equals to BM squared. BM is 4B, therefore BM squared is 4B squared, that is 16B squared, plus MQ squared. MQ is 3B, therefore MQ squared is 3B, MQ squared is 3B squared, that is 9B squared. 16b squared plus 9b squared is 25b squared. So in total we found out that bq squared equals to 25b squared. We took out of this equation and we found out that bq equals to the square root of 25, that is 5, times the square root of b squared, that is b. So in total bq equals to 5b units in its length. This is the missing side bq, that is equals to 5b units in its length. In the next step, we calculated the area of this triangle ABQ using two different methods. And then we created the equation that says that the area of triangle ABQ according to the first method must be equal to the area of triangle ABQ according to the second method. According to the first method, the area of any triangle equals to the base of the triangle, that is AQ, times the height of the base, that is MB over 2. According to the first method, the area of this triangle ABQ equals to the base, that is AQ, times the height, that is MB over 2. And it must be equal to the area of triangle ABQ according to the second method. According to the second method, the area of this triangle ABQ is equal to AB times BQ times sinus angle ABQ over 2. So again, according to the second method, the area of triangle ABQ equals to AB times BQ times sinus angle ABQ over 2. We have 2 on both sides of the equation, so 2 will get cancelled. In order to find out the value of sinus ABQ, we implemented the law of sines in our drawing. According to the law of sines, it is for any triangle. This is the triangle ABC, that will be any triangle. Side AB equals to C units in its length, side AC equals to B units in its length, and side BC equals to A units in its length. This is angle alpha, this is angle beta, this is angle gamma. According to the law of sines, the following equation is true, that A over sinus alpha equals to B over sinus beta equals to C over sinus gamma equals to 2R. 2R is the diameter of the circle that blocks this triangle, triangle ABC. We can implement the law of sines in our drawing. Why? Because in our drawing we have triangle ABQ, and triangle ABQ is blocked by this circle. The law of sines is true in any triangle, therefore it must be also true in triangle ABQ. According to the law of sines, the following equation is true, that AQ over sinus angle ABQ equals to 2R. And 2R is the diameter of this circle that blocks this triangle, triangle ABQ. According to the law of sines, the following equation is true, that AQ over sinus angle ABQ equals to 2R. Here we multiply this equation by sinus angle ABQ, and then we divide it by 2R simultaneously, and finally found out that sinus angle ABQ equals to AQ over 2R. So now we can substitute sinus angle ABQ by AQ over 2R. We did it, and we found out that AQ times MB equals to AB times BQ, and sinus angle ABQ is AQ over 2R. Here we have AQ on both sides of this equation, so AQ will get cancelled. After we cancel AQ, in this side of the equation we left only with MB, is equals to AB times BQ over 2R. Here we multiplied this equation by R, and then we divided simultaneously by MB, and we finally found out that R equals to AB times BQ over 2 times MB. So R equals to AB. AB is 8 times BQ. BQ is 5B over 2 times MB. MB is 4B. So in total we should find out that R equals to 8 times 5B over 2 times 4 times B. We have B in the numerator and B in the denominator, so B will get cancelled. We have 8 in the denominator. In the denominator we have the denominator we have 2 times 4, that is 8. So 8 we can cancel with 2 times 4, that is 8, and we left only with 5. So we can find out that the radius of this circle R equals to 5 units in its length. Our task is to find out the area of this circle. Actually, we know that the area of any circle equals to pi times the radius of the circle squared. Again, the area of any circle must be equals to pi times the radius of the circle squared. And therefore, the area of our circle must be equal to pi times the radius of our circle squared. The radius of our circle squared is r squared. So the area of our circle in total must be equal to pi r squared. But r is 5, therefore r squared is 5 squared, that is 25. So in total, there are 4 seconds must be equal to either 25 pi or 78.54 square units in size. So in both methods, we actually found out that there are this second that we are looking for this expression, it is equal to either 25 pi square units in size, or there on this second, according to both methods, is equal to 78.54 square units in size. Okay, thank you very much.